Second law of thermodynamics. In the last class, we have discussed about Clausius inequality, right? And someone is asking that uh, how we can say for a process that change in entropy is always greater than equal to dq reversible upon t. So suppose if I am taking this irreversible process, I am moving from A to B and I'm making this process cyclic by again moving from B to A reversibly. So first I move from A to B reversible and then B to A reversibly. So now this is a cyclic process. Now I can apply this Clausius inequality for irreversible cyclic process. I can write that uh, the value of dq upon t for this cyclic process should be negative, right? Because it is irreversible cyclic process. So now I can put that I can move from A to B, then A to B dq upon t plus B to A dq reversible upon t should be less than 0. And from here, if I take this on right side, integration minus integration of B by A can be written as plus integration of A to B, right? So this is dq reversible. So this is entropy change in process A to B. So entropy change in process A to B in a irreversible process should be greater than dq irreversible upon t, right? So now I can say that if my system is universe, then for universe is an isolated system. For universe, dq is always 0. So my universe is participating in irreversible process, then dq irreversible is equal to 0. If I put here, I can say that the entropy change of universe participating in irreversible process should be greater than 0. So that's why we say that if any irreversible process is taking place, the entropy of universe is going to increase. Similarly, if I take a reversible process, I'm moving from A to B reversibly and then B to A reversibly. From here also I can say that the entropy, the value of dq upon t in this cyclic process will be 0. I can write that this is equal to dq reversible from A to B plus dq reversible upon t from B to A. And if we simplify, again I can write like this. So again for universe, I can say that dq reversible for universe, because the universe is isolated. Isolated means there is no exchange of any type of energy, right? So dq reversible is going to be 0, and from there also we can say that delta S universe in a reversible process will be equal to 0. तो इसलिए हम सेकेंड लॉ को जो डिराइव करते हैं, कहते हैं कि अगर कोई रिवर्सिबल प्रोसेस होगा तो उसमें यूनिवर्स की एंट्रोपी चेंज नहीं होगी. अगर कोई इरिवर्सिबल प्रोसेस होगा तो उसमें यूनिवर्स की एंट्रोपी बढ़ेगी. These two statements are derived from Clausius inequality. Now we are discussing method of determination of entropy change for an ideal gas participating in any process. यहाँ पे first we have taken the process reversible, but what I am deriving, it is valid for irreversible process also. So I am saying that I am moving from A to B, right? A to B, either I move from A to B irreversibly or I can move through reversible process. Entropy is a state variable, so I can say that the entropy change in irreversible path is equal to the entropy change in reversible path, and that is equal to entropy final minus entropy initial. So for an ideal gas participating in any process, I am choosing the reversible path, but it is valid for irreversible also. So I have taken that an ideal gas is participating in a reversible path. Using first law of thermodynamics, I can write that du is equal to del q reversible plus del w reversible. And from here I can write that del q reversible is equal to del u minus del w reversible. Ideal gas participating in any process, du is ncv dt. And since the process is reversible, I can write that work done is minus times of P external into dV, and P external is equal to P of the system because it is reversible. So I can simplify this. I can write that this is P into dV. Minus minus will become plus. So this is del Q reversible, and now I can put the formula to calculate entropy change. So that is equal to NCV dt plus PdV upon T. And if we simplify, we can write that this is NCV dt upon T, and this is P by T. P by T can be written as nR by V by using ideal gas equation into dV. If we integrate both sides, from there we can say that we are moving from T1 to T2 and V1 to V2. This is entropy S1 and this is entropy S2. So entropy change for an ideal gas participating in reversible processes NCV ln T2 upon T1 plus nR ln V2 upon V1. So though I have derived this formula for a reversible process, but entropy is a state variable, it is valid for irreversible also, valid for irreversible and reversible both, provided I know what is the final volume and initial volume, final temperature and initial temperature. Similarly, if I want to write the entropy change in terms of temperature and pressure, for an ideal gas, I can always write that ideal gas participating in any process, if the number of moles of the gas is constant, we can write that T1 V1 upon T2 is equal to T1 is equal to P2 V2 upon T2. So using this, if I want to eliminate this volume, I can write that V2 upon V1 is equal to P1 upon P2 into T2 upon T1. And if I put this value here, then I can write that the entropy change can be written as, after simplification, I am writing NCP ln T2 upon T1 plus NR ln P1 upon P2. So in this term also I can write, or if I want to eliminate this temperature, then T2 upon T1 can be written as P2 V2 upon P1 V1. T2 upon T1 can be written as P2 V2 upon P1 V1. From there I can say that entropy change will be NCV ln T2 upon, when CV is coming, pressure will come NCV ln P2 upon P1 plus NCP ln V2 upon V1. So these are the three formulae. You can remember one and you can then convert whatever needed, right? So this is regarding entropy change of an ideal gas participating in any process. Now, an ideal gas participating in isochoric reversible process. So for that, if I am writing, I should start with ds. ds is equal to del q reversible upon T. And then I can write that if volume is constant, this is equal to NCV dt upon T. So this is the entropy change for an ideal gas participating in isochoric reversible process. And I want to draw entropy versus temperature graph for that. So you can see here that N is positive, CV is positive, right? dt NCV dt upon T, right? So from here, we can say that ds upon dt, the change in entropy with respect to the change in temperature is positive because it is NCVT. NCV upon T, these all three are positive, so this value is going to be positive. So slope of tangent on this graph is going to be positive. Then if I double differentiate it, del square S upon del T square, from there I will get that NCV is constant and differentiation of 1 by T is minus 1 by T square. So this is going to be negative. So the rate of, because this graph can be like this also. So how you will decide that the graph, this graph is correct or this given graph is correct? From here you can say that the slope is decreasing, right? Rate of change of slope is decreasing. Because of that, we can say that this is the right graph. So यहाँ पे we can frame a language, and the language is that at low temperature, if we change the temperature by small quantity, the entropy change will be more with respect to this high temperature, right? ऐसा हम chemical kinetics में कहते हैं कि low temperature पे if we increase the temperature, the rate constant value change by small quantity, while by large quantity. At high temperature, if we increase the temperature, the rate constant changes by a small quantity, right? Same way we can say like that in language, that if an ideal gas is participating in isochoric process At low temperature, if I increase the temperature by small quantity, entropy change will be more, while at high temperature, if I increase the temperature by small quantity, the entropy change will be less. Because of this, rate of change of slope is decreasing. On that basis we are saying, okay. Entropy change for an ideal gas participating in isobaric process, same way I can write here that ds upon dt is equal to ncp dt, right? We have started that entropy change is equal to del q reversible upon t. Since the process is isobaric, I can write del q reversible at constant pressure, which can be written as ncp dt upon t. So from here we can write that ds upon dt is equal to n into cp upon t, right? So this value is going to be positive. So that's why the slope on this entropy versus temperature graph is positive. Again, we'll differentiate. After differentiation, this is negative. So we can say that rate of change of slope will be negative. Same line, we can say that at low temperature in isobaric reversible process, if we increase the temperature, the entropy change will be more with respect to high temperature. So it is more sensitive at low temperature than at high temperature. An ideal gas participating in isothermal reversible process, we can write that dq reversible upon t. By using this, we can write temperature is constant, so dt is 0. So from here, ds is nr dv by v. So ds upon dv, if we write the slope on this curve, ds upon dv is nr by v, which is positive. So that's why we have decided that, okay, the slope on this curve is going to be positive, and rate of change of slope, we can see here that this is negative. So again, we can say that in isothermal process, at low volume, if we increase the volume, entropy change will be more. At high volume, if we increase the volume, entropy change will be less. Here we have written that the entropy change in this isothermal process is nr dv upon v. And by using ideal gas equation, PV is equal to nRT. So from there, I can write that P upon T is equal to nR by V. So again for isothermal process, I am putting this value, right? So we know that for isothermal process, D into, please don't talk, P into V is constant. So if we differentiate, we can write here that P into V is equal to minus times of V into dP, right? So I want to write this thing P by T. I want to eliminate this volume in terms of pressure. I want to write, right? So that's why I have written that P into V dV is equal to minus times of V into dP. So this whole thing is converted into this, because in place of P into dV, I'm writing minus times of V into dP divided by temperature. And then again, I am using that volume upon temperature. I can write this is equal to nR by P. So this is minus nR by P dP. So again, if I draw entropy versus pressure graph, right? So here on increasing the pressure, entropy is going to decrease. At temperature constant, if I increase the pressure, entropy is going to decrease. That is fine. And the slope on this graph is going to be negative. If we double differentiate, the rate of change of slope will be positive. So from there, I can decide that at low pressure, if I increase the pressure, the decrease in entropy will be more. At high pressure, if I increase the pressure, the decrease in entropy will be less, right? So these are the theoretical parts. Mathematically, we have derived that can be converted into language. This you already know that if temperature is constant, in isothermal expansion, entropy is going to increase, temperature is constant, so it is like this. In isothermal compression, it will be like this, temperature is constant, entropy will decrease. An ideal gas participating in adiabatic reversible process. So we know that isoentropic process. So if volume is increasing or decreasing, entropy is not going to change. Or temperature is increasing or decreasing, entropy is not going to change. Or we can say here that there are two ways to say that ds is equal to dq reversible upon t. Since dq throughout the process will be 0, so there is no change in entropy at any point of time on the process during the process. Or if I am writing like this, we can say that in adiabatic reversible expansion, there is cooling effect. So T2 is less than T1. So this value is going to be negative and volume is increasing. So this is positive. Then the next, Please mute yourself. So the entropy change is equal to zero, means the increase in entropy, decrease in entropy due to decrease in temperature will compensated by increase in entropy due to increase in volume. So sometimes this is also converted into language. We can say that during adiabatic reversible expansion, the increase in entropy due to increase in volume is nullified by the decrease in entropy due to decrease in temperature. Now, another important point regarding this adiabatic irreversible process, let me tell you that we know that if the process is irreversible, for irreversible process, an ideal gas is participating in adiabatic irreversible process, we know that delta S total is going to be positive. This is positive. And delta S surrounding is going to be zero because in adiabatic process, with respect to surrounding, all the processes are reversible. Suppose a system is participating in a irreversible path, right? A to B, it is moving very fast. So with respect to surrounding, this process will be slow because anything except system in the universe is surrounding. So surrounding is very large. So whatever the heat energy exchange or whatever thing which is exchange, work energy exchange with respect to system and surrounding are different. So with respect to surrounding, this is a reversible process only. So dq surrounding means whenever we have to calculate entropy change of the surrounding, we should write that this is equal to q surrounding upon temperature. We should start with here ds surrounding is equal to del q surrounding upon temperature. Temperature of surrounding cannot be changed. So if I integrate, I can write that delta S surrounding is equal to temperature is outside integration. So we can say that integration of this is equal to Q. So Q surrounding upon temperature of the surrounding. In adiabatic process, Q surrounding is zero. So we can say that delta S surrounding will be zero. Universe entropy is increasing, surrounding entropy is not changing. It means that in adiabatic irreversible process, delta S system is going to be positive. This is positive, right? Now, we are going to prove that how another way to see the same problem. Suppose an ideal gas is participating. This is pressure versus volume graph. I'm moving from initial state A to final state B by a irreversible path. This is a dotted path. I don't know the path, so that's why it is dotted. So this is adiabatic irreversible path. Adiabatic irreversible. In the last class, we have discussed that if the final volume will be same, and I am moving from the same initial state to same final volume, and the process is adiabatic reversible, then since the work done by the gas will be more in reversible process, the temperature change will be decrease will be more. And we have discussed that P final is equal to nR T final upon V final. On the basis of that, we are saying that V final is same. So T final and P final is related. T final is less in adiabatic reversible because the work done by the gas will be more. So this is adiabatic reversible and this is adiabatic irreversible. So suppose I want to calculate what is the entropy change from process A to B, which is an irreversible process. So I can say that is equal to entropy change in process A to C, and then entropy change in process C to B. Entropy change in process A to C will be zero because it is adiabatic reversible. This is isochoric process. For isochoric process, this is an ideal gas. So entropy change is dq reversible upon T. dq is ncv dt upon T. If you integrate, you will get ncv ln T2 upon T1. So Tb upon Tc. Since Tb is greater than Tc, we can say that the entropy change of the ideal gas in this adiabatic irreversible process is going to be positive. This value is going to be positive, right? So here we have proved the same thing, right? Same for compression, you can prove in the same way. During adiabatic irreversible expansion of ideal gas, the entropy increase due to increase in volume is more dominating than the entropy decrease due to decrease in temperature. I can use the same formula. Only difference is here the T2 will be different. If I am moving from A to B by irreversible path and by reversible path, the final temperature is different, right? So we know that irreversible process का जो final temperature है that is greater than reversible process. Here we are discussing that this is the final temperature of irreversible process. This is for irreversible, right? अगर ये reversible का होता तो entropy change will be zero. This is same, final and initial volume is same, and this is going to be positive. This is negative, but the whole value I know that because it is irreversible, delta S of the system is going to be positive. So I will say that the increase in this will dominate over the decrease in temperature, right? Same way we can write for compression. In case of compression, temperature will increase, so this is positive. Compression mein volume will decrease, so this is negative. So we can say that the whole value is going to be positive. So I can say that the entropy increase due to increase in temperature is more dominating than the entropy decrease due to decrease in volume. So these are the things which can be asked in terms of language. Entropy change of system surrounding an universe when an ideal gas participating in isothermal process, right? So this is isothermal reversible process. So if I'm saying that ideal gas participating in isothermal reversible process, I can write that delta S of the gas or system by applying formula NCV ln T2 upon T1 since temperature is constant. So first term will be 0. So I can write that this is NR ln V2 upon V1. In case of expansion, isothermal reversible expansion, suppose if I am discussing, so V2 is greater than V1, this is going to be positive. And since the process is reversible, you can directly write that delta S total is equal to 0. It means that delta S of the surrounding should be minus times of this. I can write minus NR ln V2 upon V1. Or if I want to justify by another method, I can say that, okay, entropy change of the surrounding means Q of the surrounding divided by temperature of the surrounding. Since the temperature is constant, temperature of system, temperature of surrounding, and that is equal to T. Here Q surrounding is always minus times of Q system. So minus times of Q system divided by temperature. Now the system is participating in a isothermal reversible process. So by using first law of thermodynamics, du is equal to 0, which is equal to del Q plus del W. So I can write that minus times of del Q is equal to del W. And del W is minus nRT ln V final upon V initial, V2 upon V1. So from there also, if you put the value, this is equal to minus will be EQ. Okay, I'm correct now. I'm writing here. This is okay. This is positive. This is going to be negative. This is minus NR ln V2 upon V1. Right? So if you add these two, you are getting the same thing. Delta S total will be 0. This is for reversible process. Suppose another point which is more important. If the ideal gas is participating in isothermal irreversible expansion. So isothermal irreversible expansion, without doing anything, we can say that universe entropy is going to be positive. Ideal gas participating in any process, I will apply the formula NCV ln T2 upon T1 plus NR ln V2 upon V1. Since temperature is constant, first term is 0. Then we can write NR ln V2 upon V1. So in expansion, this is going to be positive. V2 is greater than V1. Now, if I have to calculate, because I know that this is positive and system is fine, if I have to calculate what is entropy of the surrounding. So entropy of the surrounding is Q surrounding divided by temperature of the surrounding. Since it is isothermal, temperature of system and surrounding will be same. And then I can write this is minus times of Q system divided by temperature. But here system is participating in irreversible process. Now you can understand the importance of work. If I am moving from A to B, this is expansion, and I'm moving from A to B by a irreversible path. So work done will be what? Work done in irreversible process will be minus times of P external, V final minus V initial. So here, suppose a cylinder piston system will be there. If initially I am here and finally the piston will go here and it will stop. So gas final pressure and external pressure will be same. That's why external pressure is equal to final pressure of the gas. This is P external, and volume change means initial volume is this and final volume is this. So the magnitude of work done is area under the graph. If the same process will be there, if I'm moving from A to B reversibly, this is the graph. The graph is like this, right? Then the work done is equal to area under graph. This is for reversible process, right? So we know that if we are expanding something reversibly, the magnitude of work done in reversible process will be more. Suppose if I am saying this is minus 100 unit, here in irreversible process, the work done will be less. I can say just arbit value minus 60 unit, right? So if I have to write that, what is, if I am applying first law of thermodynamics for ideal gas, du is equal to 0. So dw is equal to minus times of del q. So here del q of the system की जगह मैं लिख सकता हूँ work done by the system in irreversible process divided by temperature. And now you can see that the work done in irreversible process is equal to work done in reversible process plus some value. This value should be positive because this is minus 100 and this is minus 60. I have to add something positive to get this value. So if I write that what is entropy change of the surrounding, that can be written as work reversible plus some positive value divided by temperature. So work reversible is minus nRT ln V2 upon V1. So I can write that this work reversible upon temperature, and this is A by temperature. This value is equal to minus nR ln V2 upon V1. And this is A by T. So if I write what is delta S total, this delta S total value can be calculated because if you add this, these two terms will cancel out. और यहाँ पे हम लिख सकते हैं this is A by T, right? This is the method to calculate the entropy change of the surrounding or entropy change of universe if the process is irreversible. They will give that how much less work is done when the process is irreversible. This A value will be given, and from there you can calculate. So this is very important. Now, same way you can write for isothermal reversible compression and irreversible compression. Same method is there. You can go through it. Now I'm discussing entropy change for an ideal gas participating in adiabatic process. For adiabatic process, if the process is reversible, ideal gas participating in adiabatic reversible process. So I can write that at any point of time, delta S of the system is equal to del Q reversible of the system divided by temperature. Since it is adiabatic reversible, del Q reversible will be 0 at each and every point. From here, I can write that entropy change of the system is going to be 0. Surrounding के लिए तो कोई भी problem नहीं है. I can always write that delta S surrounding is equal to Q surrounding upon temperature of the surrounding. And Q surrounding will be 0. So this is 0 always in adiabatic process. Either the process is reversible or irreversible, it will not affect. Now I can say that delta S total is going to be 0, right? So we can say that neither the system entropy is changing nor the surrounding entropy is changing, neither the entropy of universe is changing. That's why this is known as isoentropic process. Adiabatic reversible process is isoentropic. It is not for ideal gas. It can be for any substance because dq reversible will be 0. It is solid, liquid, or gas or real gas, whatever you can write directly. For any system, you can say that if it is adiabatic reversible, there is no change in entropy of system, surrounding, and entropy of universe. Now, if the process is adiabatic irreversible, then it is interesting. We know that if it is irreversible, delta S total is going to be positive, and delta S surrounding is always 0 for adiabatic because it is Q surrounding upon temperature of the surrounding. Q surrounding is 0, so this is 0. Now I have to calculate what is entropy change of the system. This is tricky. So you can see here that entropy change of the system can be written as del Q reversible upon T. I cannot put del Q because this process I am moving from A to B. This is pressure versus volume graph. This is pressure versus volume graph, but I cannot put this dq reversible. I know that it is dq irreversible is equal to 0. But whenever I have to calculate entropy change, I will choose a path which is reversible. So I am choosing another path. I will move from here to here, same final volume by adiabatic reversible path, and then I can move from C to B by again a reversible path. This is isochoric reversible path. So now if I have to write that what is entropy change of the system, right? I have to use this part to calculate the entropy change in irreversible process. So we know that entropy change here, if I am writing that what is entropy change in process A to B, which is equal to entropy change in process A to C plus entropy change in process C to B. A to C is adiabatic reversible, so that is equal to 0. But this is isochoric process, so I can write this is NCV ln final temperature upon initial temperature TC, and final temperature is greater than initial temperature. I can say that the entropy change here is positive. So system entropy is increasing, universe entropy is increasing, there is no change in the entropy of the surrounding, right? So we can say that in any adiabatic process, there is no change in entropy of the surrounding. There is no adiabatic process in which the entropy of system is going to decrease. If the process is reversible, it will not change. If it is irreversible, the entropy of system is going to increase. So there is no adiabatic process in which the entropy of the system can decrease. And the last point is in adiabatic process, if it is reversible, then the entropy of system surrounding and universe remains. If it is reversible, then the entropy of system surrounding and universe will be same, and that's why it is known as isoentropic process. Now this is free expansion of an ideal gas, Joule's experiment. There are two experiments with the name Joule's. एक है Joule's और एक है Joule Thomson. Joule Thomson हमारे syllabus में नहीं है, right? But Joule's experiment is there in our syllabus और JEE Advanced में इससे क्वेश्चन पूछे गए हैं. तो already we have discussed that external pressure will be zero, so work done will be zero. By doing experiment, we come to know that there is no exchange of heat energy, so Q will be zero. So by using first law, we can say delta U will be 0. Delta U is NCV delta T, so delta T will be 0. Delta H is NCP delta T. Since delta T is 0, delta H is equal to 0. Now I am using what is the entropy change. So an ideal gas participating in any process, I can write NCV ln T2 upon T1 plus NR ln V2 upon V1. So here there is no change in temperature. This term will be 0. And here this is NR ln V2 upon V1. So they can ask a question, because this free expansion, there is no exchange of heat energy between system and surrounding. When this process is happening, the gas is moving from a chamber to vacuum, right? Here there is gas and this is vacuum. So the gas is moving from here to here. There is no exchange of heat energy, still the entropy is increasing. So some student get confused कि dq तो zero है, dq irreversible zero है. If the same process is carried out reversibly, then dq must be positive. Then only we can say that entropy is going to increase. So they can ask a question that if there is no exchange of heat energy between system and surrounding, can the entropy of the system can increase? Yes, it can increase. It can increase in adiabatic irreversible process, right? Delta S system, you know, delta S surrounding will be 0 and delta S universe is equal to delta S of the system. So this is a question based on Carnot cycle. We are saying that prove that if efficiency, theoretical efficiency of Carnot cycle is 1 minus T2 upon T1. Right. So the point is that by doing this question, you should know that if we draw temperature, entropy versus temperature graph, here entropy versus temperature graph we are going to draw. And for Carnot cycle, we already know pressure versus volume graph. We are moving from A to B by isothermal expansion, then B to C by adiabatic expansion, C to D by isothermal compression, and D to A by adiabatic compression. So if I try to draw this graph A to B, if I'm moving from A to B, volume is increasing, temperature is constant, NR ln V2 upon V1. So we can say entropy is going to increase. So when I'm moving from A to B, I can write like this. Moving from B to C mein, there is no change in entropy, adiabatic reversible, but temperature is decreasing. So I should move from here. This is B to C. Then I am moving from C to D. It is isothermal process. Since it is compression, the entropy will decrease and temperature will remain constant. So this temperature is T2 temperature, this temperature is T1 temperature, and finally there is no change in entropy, but temperature is increasing. So this is the graph. Now this I can assume that this is entropy S1 and this is entropy S2. Now I have to calculate efficiency. Efficiency is equal to magnitude of work done in cyclic process upon heat supplied. So you know that del ds is equal to del q reversible upon temperature. So whenever you have to see the sign of del q, you should write TDS. By looking the sign of change in entropy, we can comment about the sign of dq. So if I'm moving from A to B, the entropy is increasing. So I can say that here del Q is positive. This is positive, and this is Q1. When we have studied about this Carnot cycle, this is Q1, which is positive. Then this Q will be 0, right? This, if you see that I'm moving from C to D, temperature is constant, but entropy is decreasing. So here we can say this is Q2 and this is going to be negative here, Q2, which is negative heat rejected by the system. When we try to draw graph, right, projection, we'll take projection on entropy axis. जैसे work done में volume axis पे था, वैसे ही यहाँ पे entropy axis. So from A to B, work done is area under the graph where the projection is taken on entropy axis and entropy is increasing. So this whole thing is going to be positive. From C to D, we can say that entropy is decreasing. So this line के नीचे जो area है ये वाला, this is going to be positive. So we can say that in this whole cyclic process, Q of the cycle is area enclosed and that is going to be positive. तो अगर मैं यहाँ पे Q cycle is magnitude of work cycle, तो यहाँ से अगर मैं value लिखता हूँ, so I should write positive value. Area of this rectangle will be length into width. So हमें sign का ध्यान रखना, it should be positive. S2 is greater than S1 and T1 is greater than T2. So we can write here T1 minus T2, right? So this is the magnitude of work done in cyclic process. If I write what is heat supplied, this whole thing is heat supplied. That is T1 into entropy change S2 minus S1 will be heat supplied. So this will cancel out. We are able to prove 1 minus T2 upon T1. Sometimes in question, in order to calculate efficiency, they can draw temperature versus entropy graph and they can ask question based on this. Now, entropy change on mixing of two non-react. Please mute yourself and then talk. Entropy change on mixing of two non-reacting ideal gases at constant temperature and pressure. This is a very common question, right? अब इसके different cases है, उसको हमें discuss करना है. तो first we should understand that what we are talking here. Suppose we have an ideal gas, mixing of two ideal gases. They are two different gases. We are talking about two different gases. So the gas in container, this container is gas A. The number of moles of this gas is Na. It is present at pressure P and temperature T, right? The volume of this container may be anything. It can be Va, right? Here B gas is there. Number of moles of this gas is Nb. Pressure is same, that is P, and temperature is T. Volume can be anything, Vb. You can calculate volume by using ideal gas equation. Now what we are saying that we want to mix these two gases. They are two different ideal gases. So when we are going to mix them, means if I remove this stopcock, the pressure of the system should not change. Constant temperature and pressure mein the pressure of the system should not change. Pressure of individual gases will decrease because their volume is increasing and temperature is not changing. So here temperature will remain T. Here also temperature will be T. Gas A is present in both containers. So now I will write partial pressure of gas A. Gas B is present in both containers. So partial pressure of gas B. So sum of partial pressure of both gases is equal to the initial pressure. Then only we can say that the pressure of the system is not changing. Initial pressure here is P, and finally here is also P. So constant pressure and temperature का मतलब ये है. This will remain Va and this will remain Vb. So we can solve this question in many ways. Like one thing I can say that the change in entropy during mixing is equal to the entropy change of gas A plus the entropy change of gas B. Entropy change of gas A, I can apply many formula. I am using that Cp formula. So n Cp ln T2 upon T1, right? So T2 upon T1 and T2 are same. Here initial temperature and final temperature are same. So this term will be 0. N R ln P1. P initial is P, and now for A gas final pressure is partial pressure of A. So obviously partial pressure of A is less than total pressure. So this value is greater than 1. This is going to be 0. We'll say that this is going to be positive. So entropy of gas A is increasing. I can further simplify this. I can write that we know that partial pressure of gas A is equal to mole fraction of gas A into total pressure. So by using that, I can write that this value P upon partial pressure of A is equal to 1 by XA. So we can write in that form also, but that is going to be positive. Similarly, I can write entropy change of gas B is equal to NR ln initial pressure of B upon final pressure of B, which is also positive. Or if we say what is delta S mixing, I can write that delta S mixing is equal to NR, I can take common. And this is ln 1 upon mole fraction of A, and this will be ln 1 upon mole fraction of gas B. So now you can simplify, you can write that this is minus n, here Na, sorry. So I have done mistake here, number of moles of A, and here number of moles of B will be there. So I cannot take n common, and should be inside. So number of moles of gas, number of moles of gas B, and then I can multiply and divide it by n total. I am multiplying here by n total and dividing here by n total. So now n total R will be common, and n total को अंदर ले जाऊंगा तो Na upon n total is mole fraction of A ln XA, mole fraction of B ln XB. So this is the form in which you can convert. Or some of you can use the other formula, other method to calculate the same thing. I can write that delta SA is equal to n CV ln T2 upon T1, which is 0. Then n R ln V2 upon V1. V2 is VA plus VB. Now the gas is present in both container, and initially it was in A container, right? Similarly, the entropy change of gas B will be NB into R ln. Final volume will be VA plus VB, and initial volume will be VA. And now you can put the value. VA is equal to what? NA RT by P. And VB is what? NB RT by P. And if you simplify, you'll get the same thing. By using this also, you are going to get the same thing. Now, there is a very interesting question based on this, which is known as entropy discrepancy. कुछ ऐसा word use करते हैं हम, इसको कहते हैं, let me use the word entropy catastrophe, right? So what is entropy catastrophe? I am explaining that a vessel is divided into two compartments of equal volume by a partition. Each compartment contains 1 mole of same absolutely identical gases at the same temperature and pressure. The partition is removed and the gases are allowed to mix. Calculate the entropy change during this process, right? So here you can see that this is the same gas at pressure P and temperature T. This is also identically the same gas as pressure P and temperature T. If you are going to remove, obviously gas same hai, pressure same hai, so pressure is not going to change, temperature is not going to change, right? So this is the situation, this is the initial condition, and this is the final condition. Now some of you, since you will apply the formula NCV ln T2 upon T1, this entropy formula NCV ln T2 upon T1 plus NR ln P1 upon P2. You will use this formula. So temperature is not changing. You are fine that, okay, this will be 0. What about the pressure? Pressure is not changing. If I am writing that, what is the entropy change for the gas present in this part? Initial pressure of this is P, and this is also P. Gas is same, so pressure is not changing here. So here P1 and P2 is same. This value will be 1. So this is also equals to 0. If the gases are different, then the pressure will change. If the same gas is there at the same pressure, on removing this, pressure of the gas is not going to change. So P1 and P2 for the gas will remain same. So this is a tricky question. इसको हम कहते हैं same gas है, केवल हमने partition को हटाया है. If two different gases will be there, then on removing that, entropy is going to increase, right? That is mixing of two different gases. Here there is no different gas, same gas is there, and you are removing the partition, so there is no change in entropy. So this is a very tricky question, right? And now we are coming to different cases of mixing. जेई आई थिंक मेंस या पहले ओलंपियाड में क्वेश्चन पूछा गया है. दिस इज वेरी कॉमन क्वेश्चन दैट प्रूव दैट द इंट्रोपी चेंज ऑन मिक्सिंग ऑफ टू नॉन रिएक्टिंग आइडियल गैसेस. दो डिफरेंट गैसेस हैं और नॉन रिएक्टिंग है एट कांस्टेंट टेम्परेचर एंड प्रेशर will be maximum when the mole fraction of A and B is equal to half. Means the number of moles of gas A is equal to the number of moles of gas B. So mathematically you can solve that. You have already derived this formula. Delta S mixing is minus N total into R XA ln XA plus XB ln XB. And we know that XB can be written as 1 minus XA. दो ही gases हैं, तो mole fraction of B is 1 minus mole fraction of A. Here I have written. Now there is only one variable, that is XA. Differentiate delta S mixing with respect to XA and simplify it. From there you will get that mole fraction of gas A is half, so mole fraction of gas B is half. तो ऐसा क्वेश्चन पूछा गया था कि ये तभी वैलिड है जब एन टोटल की वैल्यू सेम है. सो एन टोटल सपोज 10 है और मैं एक बार 9 ए गैस के 9 मोल्स मिक्स कर रहा हूँ विथ बी के 1, या मैं ए के 8 मिक्स कर रहा हूँ और बी के 2 मिक्स कर रहा हूँ, या ऐसे ही हम चेंज करते करते ए के 5 और बी के 5 मिक्स करेंगे. सो द कंडीशन व्हेन द नंबर ऑफ मोल्स ऑफ ए एंड बी विल बी इक्वल, the entropy change on mixing will be maximum. और वो maximum value भी आप इस फॉर्मूले में पुट करके निकाल सकते हो. यहाँ हाफ होगा, यहाँ लॉन हाफ होगा, यहाँ हाफ होगा, लॉन हाफ होगा, राइट. सो यू कैन से दैट दिस इज लॉन हाफ, क्योंकि हाफ और हाफ 1 हो जाएगा. दिस इज लॉन हाफ, और यू कैन राइट दिस इज प्लस एन आर लॉन 2. डेल्टा एस मिक्सिंग की जो मैक्सिमम वैल्यू होगी, दैट मैक्सिमम वैल्यू इज इक्वल टू एन आर लॉन 2, राइट. So this is another thing which you should know. ठीक है, ये ग्राफ से हमने शो करके दिखाया n total into r ln 2. So delta S mixing per mole divided by r is equal to ln 2, which is equal to 0.7. तो यहाँ पे ये ध्यान से देखो, और ये मैक्सिमम यहाँ पे आ रहा है when the mole fraction is 0.5, right. So now we are discussing entropy change of system surrounding an universe participating in a phase transition. Suppose this is water and we are at point A. So you can see that this is 1 atm and this is solid and liquid, and this point on this line is melting at melting point. This is normal melting point. Pressure is 1 atm, temperature is 0 degrees Celsius, normal melting point. So if I have to calculate what is the entropy change of the system at point A, right? Melting at point A means we are saying that H2O in solid state is converted into H2O in liquid state. Pressure is 1 atm and temperature is 273 Kelvin, 273.15 or 273 Kelvin, 0 degree Celsius. तो सिस्टम एंड सराउंडिंग इज एट इक्विलिब्रियम. तो यहाँ से मैं डायरेक्ट कह सकता हूँ कि डेल्टा एस टोटल की वैल्यू 0 होगी. जब इक्विलिब्रियम होगा तो डेल्टा एस टोटल की वैल्यू 0 होगी. Now delta S system, I should start with ds. ds is equal to del q reversible upon t, and since pressure is constant here, so I should write del q p upon t, and then I will integrate. When melting is taking place, temperature will not change. आपको पता है ना कि मेल्टिंग में टेम्परेचर चेंज नहीं होगा, तो इसको बाहर ले लेते हैं. तो आई कैन राइट दिस इज इक्वल टू qp upon t, या qp upon t like this, right? So entropy change is equal to qp upon t, and qp is equal to delta h upon t, right? qp is delta h, so delta h upon t. या कुछ लोग ऐसा कह सकते हैं कि डेल्टा g is equal to delta h minus t delta s. There is an equilibrium, so delta g will be 0. So from there I can say entropy change during this will be delta h upon t. So from here now I can say that delta S system, because heat is given to the system, so delta S system or Q system is going to be positive. Temperature in Kelvin is positive, so delta S system will be positive. Delta S total will be 0. It means that delta S surrounding is going to be negative. So you can tell about the sign कि हम अगर मेल्ट कर रहे हैं तो हीट एनर्जी देंगे. सिस्टम की हीट एनर्जी ले रहा है तो सराउंडिंग लूज कर रहा है, तो सराउंडिंग की इंट्रोपी डिक्रीज करेगी. सो फ्रॉम हियर इफ आई वांट टू right, we can say delta S system will be positive, delta S surrounding will be negative, delta S total is equal to 0. Now, the second point, boiling at point B, same way we can say boiling is taking place at boiling point, equilibrium will be there. So we'll say that equilibrium is there, then delta S total will be 0. I can directly write here, delta S total should be equal to 0. Boiling के लिए we are giving heat energy to the system. Same way I can write delta G will be 0. So delta S vaporization is equal to delta H vaporization divided by boiling temperature, which is positive. So entropy of system will increase. If system is gaining heat energy, surrounding is losing heat energy, so delta S surrounding is going to be negative. So A और B का आंसर सेम है. Now discussing this C and D option. D option, C option को पहले डिस्कस करते हैं. Here liquid state is stable and they are talking about melting at point C. तो C point पे अगर हम melting की बात करते हैं, we are talking here H2O melting, H2O solid and H2O liquid, where the temperature temperature is 0 degree Celsius but pressure is greater than 1 atm. Pressure की value 1 atm से बड़ी है. Now here liquid state is stable, so if I bring the solid over here, it will itself converted into liquid. So we can say that this is a spontaneous process. Delta G of this process will be negative, right? एक चीज यहां से ये भी लिख सकते हैं कि डेल्टा जी इज इक्वल टू डेल्टा एच माइनस टी डेल्टा एस, एंड डेल्टा जी की वैल्यू नेगेटिव है, सो वी कैन राइट दैट डेल्टा एच इज ग्रेटर लेस देन टी डेल्टा एस, और वी कैन से दैट एंट्रोपी change in this process will be greater than entropy of vaporization divided by temperature. तो वही सेम ही है ना, 0 डिग्री सेल्सियस. तो ये इक्विलिब्रियम वाले इस वाले इंट्रोपी से ये वाला जो इंट्रोपी चेंज होगा सिस्टम का वो ज्यादा होगा, दैट वी कैन प्रूव, राइट. और वी कैन से मेल्टिंग हो रही है, सिस्टम हीट एनर्जी ले रहा है, तो सिस्टम की इंट्रोपी तो गोइंग इट इज गोइंग टू इंक्रीज, सराउंडिंग की इंट्रोपी इज गोइंग टू डिक्रीज बिकॉज सराउंडिंग इज लूजिंग हीट एनर्जी. एंड टोटल के लिए हम कह सकते हैं इट इज इरिवर्सिबल प्रोसेस, तो इंट्रोपी ऑफ यूनिवर्स इज गोइंग टू बी पॉजिटिव, राइट. सो दीज आर द थिंग्स यहां डिस्कस करते हैं. वी आर डिस्कसिंग बॉइलिंग हियर अगेन. इफ वी टेक at D point, if we take H2O in liquid state and we are discussing boiling H2O in gaseous state, again gas is stable here, so directly this will convert into gas, means this is a spontaneous process. So either you can use like this or you can directly say that ds is equal to del q upon t. सिस्टम की बात हो रही है, अगर ये गैस में जा रहा है लिक्विड से तो ये एंडोथर्मिक प्रोसेस होगा, दिस शुड बी पॉजिटिव. सो आई कैन से दैट एंट्रोपी ऑफ सिस्टम, entropy change of system is positive, entropy change of surrounding heat energy system को दे रहा है, so it will be negative, and since it is irreversible process, delta S total is going to be positive. So this is the way to see. Sometimes you can use this to get some value ki delta S system should be greater than this value and all that.
So during the process be means reversible because it can again freeze and come back to the solid state. So why is it irreversible?
Which one beta?
So the D state. I'm talking
Ah,
about the D.
at D state gas is stable, na? Why it will go back?
No, but at a okay, you're considering at that state only, right, sir?
Ah, this point.
Yes,
At
sir.
this point gaseous state is there, na?
Yes, sir. All right, sir. Thank you, sir.
Now we are discussing something about thermochemistry. It is not. There are two things which is important for thermochemistry. One is you should be very thorough with the definitions. क्योंकि जब जे एडवांस में जब भी क्वेश्चन पूछे गए हर अल्टरनेट ईयर में थर्मोकेमिस्ट्री से एक सवाल आता है जो कि बहुत ही इजी और कॉन्सेप्चुअल होता है. तो यू हैव टू टेक केयर ऑफ टू थिंग्स. You should know the definitions properly, and the second thing is the question is very easy, so you have to give time to the question to do plus and minus. ये दो अगर आप संभाल लोगे तो थर्मोकेमिस्ट्री का क्वेश्चन सॉल्व हो जाएगा. सो आई एम डिस्कसिंग सम इंपॉर्टेंट पॉइंट्स रिगार्डिंग थर्मोकेमिस्ट्री जो जेई में क्वेश्चंस पूछे जाते हैं. कैलोरीमीटरी से बहुत ज्यादा क्वेश्चन पूछे जाते हैं. यू शुड बी वेरी श्योर अबाउट कैलोरीमीटर, राइट. सो calorimeter is an instrument to measure the heat exchange during a chemical or physical process. ये एक instrument है. So there are two type of calorimeter. One is bomb calorimeter and the other is cup calorimeter. बॉम्ब मीन्स वॉल्यूम इज कांस्टेंट. बॉम्ब जो ब्लास्ट होता है वो इसलिए ब्लास्ट होता है क्योंकि उसको बाहर निकलने की जगह नहीं मिलती एंड इट ब्लास्ट, राइट. सो इन केस ऑफ बॉम्ब वॉल्यूम इज कांस्टेंट. इन केस ऑफ कप, कप कैसे चाय पीते हैं अगर हम कप में, तो अब ओपन कंटेनर होता है, ओपन कंटेनर में प्रेशर कांस्टेंट होता है. सो फ्रॉम देयर यू कैन लॉजिकली अंडरस्टैंड दैट cup is pressure constant and bomb is volume constant. So when we do when we do use bomb
ఏమన్నా
calorimeter,
కదా నిన్న కోసం ఏది ఆన్లైన్
म्यूट म्यूट करके बात करिए. Okay, so what we are saying here, bomb calorimeter means there is a container in which chemical reactions, जो भी reactions के लिए हमने जो reactant है उसको mix किया है, when this reaction will happen and suppose this reaction is exothermic, so heat energy will release. So when heat energy will release, the temperature of this box, and here water is there, the temperature of water is going to increase. Stirrer is there so that the temperature, heat energy will be uniformly distributed. There is a thermometer. So with the help of thermometer, we'll know that what is the rise in temperature, and they will directly or indirectly, they will give that what is the heat capacity of the whole system. Whole system means this small container, whatever the things left in that, and this water. So they will combinedly, sometimes they will combinedly give, sometimes they will separately give. You have to be very careful about that. So whatever the heat energy liberated at constant volume, you can write that is equal to heat capacity into delta T. Delta T will be given, heat capacity will be given. Then you can calculate what is the heat energy exchange. And they have mentioned that what amount of substance is reacting so that this heat energy is releasing. And then if you know the definitions, you can solve the question, right? So this is about bomb calorimeter. Similarly, about cup calorimeter, which is taking place in open container. The concepts are similar. You should be careful to note that what is the heat capacity of calorimeter. Suppose this is a question, I will try to explain you how to follow the question, right? When 1 gram of fructose and is burned in oxygen in a bomb calorimeter, the temperature of the calorimeter water increases by 1.56 degrees Celsius. If the heat capacity of the calorimeter and its constant is 10 kilojoule per degree Celsius, they have given the heat capacity of the whole system, this plus water, सबको मिला के दिया है. So we can find out Q. Q is equal to heat capacity into change in temperature. Calculate the heat of combustion of fructose at 298 Kelvin in kilojoule per mole at constant volume and constant pressure. So first thing is that you should write fructose combustion reaction. So for fructose formula, glucose and fructose are same thing, they are isomers. So C6H12, O6 formula will be same, in solid state is subjected to combustion. Now you should know that what is the heat of combustion. It means that 1 mole of the substance which is subjected to combustion is reacting with sufficient or excess amount of oxygen to form the corresponding product. So here the product will be CO2 in gaseous state and H2O depending upon temperature, right? So we are doing the experiment. Suppose this is initially at 298. So and finally we are measuring at 298, and we can say that enthalpy is a state variable. So either in between the temperature is rising, but if the initial and final temperature will same, in enthalpy change will be same. So that is the idea. So here carbon we can multiply by 6, hydrogen we can multiply by 6, oxygen we can count here. So this is 12 and this is 6 already. So 6 will be there. This is the balanced reaction, right? I'm writing at 298 Kelvin where the water is present at. So in actual, what is happening when the reaction is going, the temperature will rise, but that is the beauty of enthalpy change. Enthalpy is a state variable. Initially, this whole system has 298 Kelvin. When the reaction is finished, the product is at 298 Kelvin, right? So that's why I can write that what is the enthalpy here initial and what is the enthalpy here final, and we can write delta H, right? Like that. So this is heat of combustion. First thing you should know about this. Now I am using that we are doing experiment in a bomb calorimeter. So heat exchange taking place at constant volume. should be equal to the change in internal energy of the system. QV is delta U, and QV can be written as heat capacity into यहाँ minus sign, because if heat is rejected, then only the system is gaining. So system is gaining heat capacity into temperature change. That is the heat energy absorbed by the surrounding, and this is the heat energy released by the chemical reaction. So I can write like this. So I know what is delta U of the reaction, right? By doing calculation, they have given that for 1 gram of fructose, right? So this is happening. This whole thing is happening for 1 gram. I convert this into moles. Number of moles of fructose will be 1 divided by glucose or fructose का molar mass same होता है, right? So what is that? I think 180, right? So this is the number of moles of that. So for this mole, heat of combustion they are asking. So what you will do, whatever QV is coming for 1 mole, you have to 1 by 80 mole for 1 mole, you have to multiply it by 180. So this will be the answer. This is delta U of the reaction. Now, if I have to calculate what is delta H of the reaction, I know that this is delta U of the reaction with minus sign, right? This is minus sign already there, right? Okay. So this is delta U of the reaction. Now I will use delta U, delta H is equal to delta U plus P delta V. They have not mentioned anything about initial and final pressure or volume. So I am going to assume ideal gas, and I can write delta NG RT. And delta Ng for this process will be 0. So we'll say that delta H is approximately equals to delta U. So both answer will be same. So like that you have to follow. You should know what is the reaction taking place. Your concept should be clear, right? So you can see the solution later on. अभी तो आगे बढ़ते हैं. So this is about calorimeter, right? Now there are many heat of reactions. Heat of reaction means what? It is the amount of heat energy evolved or absorbed when the number of moles of reactant equal to their stoichiometric coefficient react completely to form the product. Suppose this reaction is given, and in front of this reaction we are writing delta U is equal to minus a kilojoule per mole. So what is the meaning of kilojoule per mole? Kilojoule per mole means this is a unit of writing delta U or Q of the reaction. It means that according to the balance reaction, means when 2 moles of A will completely react with 3 moles of B to form 4 moles of C, then whatever the heat energy rejected in this process will be a kilojoule per mole, means according to the balance reaction. It doesn't means 1 mole of reactant or 1 mole of product. It means one balance reaction के according ही ये per mole का मतलब ये होता है, right? It is not related to reactant and product. It is related to stoichiometric coefficient of reactant as well as product in the balance reaction, right? Factors affecting the heat of reaction. We know that we have studied main internal energy and enthalpy, and we are saying that ideal gas change in internal energy only depends on temperature. Change in enthalpy only depends on temperature, but for solid, liquid, and real gas, the internal energy change or enthalpy change not only depends on temperature, it also depends on pressure or volume or state of matter. So condition in which the reaction is taking place. If the reaction is taking place at constant volume, then we'll say that Q reaction is equal to delta U reaction. If the reaction is taking place at constant pressure, then we'll write that Q reaction is equal to delta H reaction, right? One thing is that under what condition the reaction is taking place. Either the reaction will take place at constant pressure and temperature, or the reaction will take place at constant volume and temperature. Here, if it is constant pressure and temperature, then we'll say QP of the reaction is equal to delta H of the reaction. And here we'll say that QV of the reaction is equal to delta U of the reaction. Then physical state as well as the phase of reactant and product. Many questions based on this conceptual things will be asked. Like this is the reaction. This is what? This is formation of 1 mole of CH4. 1 mole of CH4 is formed from its constituent element. That is understood. They have not mentioned that what is this carbon. It is understood this is graphite. So 1 mole of graphite when react with 2 moles of hydrogen gas to form 1 mole of CH4. This is heat of formation of CH4. So this is delta H1. If I take this solid in gaseous state, this delta H and this delta H will be not same, because the state of matter change, delta H will same, because enthalpy of this will depend on state of matter also. right? Similarly, here carbon solid graphite, carbon solid diamond. Here the phase is different. Here one carbon atom is attached with 3. Here one carbon atom is attached with 4. Again, the internal energy and enthalpy of this will also depend that how the carbon atom is going to attach. So delta H of this reaction and this reaction will be different. So be careful about the state of matter or phases while finding out what is delta H of the reaction. Temperature at which the reaction is going to take place, because we are going to study about Kirchhoff's law. Kirchhoff's law क्या है? Variation of heat of reaction at with temperature. So suppose I'm saying that reaction is taking place at constant pressure, then at temperature T2 it is delta H2, and at temperature T1 it is delta H1. Delta H2 minus delta H1 is equal to delta Cp reaction T2 minus T1. So this is known as Kirchhoff's law. If the reaction is taking place at constant volume, then I will write delta U2 minus delta U1 is equal to delta CV reaction T2 minus T1, right? This is Kirchhoff's law. This is also related to entropy change, right? We'll study later. So temperature at which the reaction is taking place, that is also important. Now standard state, already I have discussed that there is no fixed temperature for standard state. राइट जी नॉट का मतलब है प्रेशर 1 बार होना चाहिए. टेम्परेचर कुछ भी हो सकता है, 298 हो सकता है, 300 केल्विन हो सकता है, 500 केल्विन हो सकता है. तो दिस क्वेश्चन इज आल्सो इंपॉर्टेंट. there is no fixed temperature for standard state, but if nothing is mentioned about temperature, we assume that the temperature is 298 kelvin, because we do experiment at room temperature. That's why we take this value if nothing is mentioned. The standard enthalpy of reaction is the enthalpy change for the reaction when all the participating substances in their standard state. We have studied about delta G naught of the reaction, right? Now they are asking about delta H naught of the reaction. That is also clear that when I am writing delta H naught, this is H naught of product minus H naught of reactant. Suppose this is the reaction. H naught of reactant means this substance is pure, means it is not a mixture, it is separate. Its mole is 1 and it is present at 1 bar. Then I will say that whatever the enthalpy is, the enthalpy of 1 mole of CH4, standard molar enthalpy of CH4. Then I will say that here 2 moles of oxygen is there, and the pressure of this 2 mole of pure oxygen is 1 bar. So here we'll say that the enthalpy of total oxygen is 2 times the molar standard enthalpy of oxygen molecule. And finally, again here, when we are defining not, it means that the substance should be present at 1 bar and the substance should be pure, right? So we have already discussed about this in delta G naught. Now you can understand what is the meaning of delta H naught of the reaction. So after these 2 points, we'll stop. मैं ये share कर दूंगा notes, आप पढ़ लेना. The standard state of a substance at a specified temperature is its pure form at 1 bar. For a standard state of a substance present in solution at a specified temperature is when the concentration should be 1 mole per liter. Already we have discussed that अगर कोई mixture होगा, जैसे acetate will react with water to form acid and alcohol, then we write Kc naught as concentration of alcohol divided by 1 mole per liter, concentration of acid divided by 1 mole per liter divided by concentration of ester divided by 1 mole per liter. So for mixture, the standard state concentration will be 1 mole per liter. For pure substance, it is 1 bar, right? This is it. आप एक बार देख लेना periodic table में at standard state condition only mercury and bromine are liquid. Hydrogen, nitrogen, oxygen, fluorine, chlorine, and all the noble gases are gases at 298 Kelvin and 1 atm, and all the other elements are solid. So this is about, because JEE advanced में ऐसा कुछ क्वेश्चन पूछा गया था कि डेल्टा G naught formation of bromine in gaseous state will be 0. It is correct or not? So you should know that fluorine is gas, chlorine is gas, but bromine is liquid at room temperature and iodine is solid. So these are the most stable state of aggregation. They are elemental form. But state of matter is also important. At room temperature, bromine is liquid. So this is incorrect. Delta G naught formation of bromine in gas is not equal to 0. Bromine in liquid is equal to 0. Right? So आज बस इसको यहीं पे ख़त्म करते हैं. टुडे वी आर गोइंग टू कवर, so whatever the notes are there, I will share with you. So two things are important, right? You should revise the definitions, and while solving the question, give time and do the calculation properly.
Could you send this in Kaveri Bone also, sir?
What? एक बार फिर से repeat करो.
So could you send this in CO Kaveri Bone group also?
I cannot send at different, right? I am sending to the same WhatsApp link, right? On the WhatsApp group where this Zoom link is there now, I am sharing at the same, right? Now you discuss with your coordinator. You will get ना. जैसे आपने Zoom link ज्वाइन करी है ना, उसी WhatsApp पे मैं भेजूंगा.
Sir, could you please send the link to the group in chat, sir? I want to join that group, sir.
तो मैं नहीं भेज सकता, एडमिन मैं नहीं हूँ, है ना? प्रसाद सर हैं.
Okay, sir.
ओके,
Yes, sir.
आइदर यू
Thank you.
डिस्कस विथ योर कोऑर्डिनेटर, राइट? वहाँ पे जो भी कोऑर्डिनेट कर रहे होंगे ना, तुमने ज्वाइन किया तो किसी ने लिंक तुम्हें दिया होगा ना बेटा.
Yes, sir.
तो
Yes, sir.
उन्हीं से तो सेम ग्रुप में ही है वहाँ पे. आप उनको बोलो कि मतलब कि जो जो भी इसमें क्लास नोट्स हैं वो मैं शेयर करता हूँ, वो वहाँ पे आप देखोगे तो मिल जाएंगे.
Yes, sir. Thank you, sir.